So we're going to put everything together now to help us sketch functions. And as we've seen, we can use calculus to help us do that. We can get all the important aspects of the curve. And so we'll look at the following characteristics of a graph. The domain, so what we're interested in is, are there any restrictions on the variable? We can find the intercepts algebraically. Remember, you all good?
Hey, how you doing?
X-intercepts are where y is 0, y-intercepts are where x is 0. We will only use the symmetry if it's a last resort. If after we've done everything else, we're still not 100% sure what the graph looks like, then we'll use that symmetry. Remember, symmetry is if f at negative x is equal to f at x, then it's symmetrical about the y-axis. Y equals x squared is the simplest example of that. If f at negative x equals negative f at x, then it's symmetrical about the origin. But again, we'll only use that if we absolutely need it. Asymptotes, so they come from rational functions. The denominator, the non-permissive values of the denominator tells you what the vertical asymptote is, and some rational functions have, well, they all have horizontal asymptotes as well. We'll talk about the intervals of increase and decrease, which we use the first derivative for, and we can also find our local max and mins using the first derivative. We've also seen that we can use a second derivative to find max and min points, but we also use a second derivative for points of inflection. So those are all the things that we will look at. So we want to sketch this function. This is a third degree polynomial. The initial term coefficient is positive. Because the degree is odd, we compare it to a line. A line with a positive slope falls left and rises right. This will do the same thing. This graph will fall to the left and rise to the right, which means that the first interval, it will be increasing, and the last interval, it will be increasing as well. Okay. We've also seen examples where some graphs always increase, where there is no max or min, right? So you can't always assume that the middle interval will be falling. Can't always assume that. We use derivatives to determine. Right, so because there is no denominator here, there are no restrictions. Our domain would be all real numbers. There's no restrictions. Right, so that's the first thing. Intercepts. Our x-intercept is where y equals 0. It's where x cubed plus x squared minus 2x equals 0. And there's a common factor of x here that we can take out, which is nice because then we don't have to use synthetic division. We're left with a quadratic, which factors to x plus 2, x minus 1. So our x-intercepts are 0, -2, and +1. And because 0 is an x-intercept, that's also our y-intercept as well. Our y-intercept will also be at 0, 0. Because there's no denominator, there are no asymptotes here. And to find our intervals of increase and decrease, we differentiate. So dy by dx will be 3x squared plus 2x minus 2. This quadratic is not factorable. So to find our critical numbers, we will use the quadratic formula. Negative b plus and minus the square root of b squared minus 4 times a times c all over 2a. So x will be negative 2 plus and minus the discriminant 2 squared minus 4 times 3 times negative 2. Our discriminant is 28. And we can reduce that a little bit because root 28 breaks down to root 4 root 7 or 2 root 7. All over 6. And now all three terms are divisible by 2. We'll get negative 1 plus or minus root 7 over 3, which are the exact values of our critical numbers, but we need to know what they are as a decimal so that we can set up our intervals on the number line. So if you plug those into the calculator, you will get approximately negative 1.2 and 0.5. Approximate. 1.2, negative 1.2. So again, these give us our number line. Here are our critical numbers. And the number to the left of negative 1.2 would be negative 2. And we let x equal negative 2 in the derivative. Negative 2 all squared is 4 times 3 is 12. 2 times negative 2 is minus 4 minus 2. That's a positive value, so like we said, the function is increasing in that interval. We can use 0 as a number in the next interval, and when x equals 0, we'll get negative 2, so the function is decreasing there. And after 0.5, a number like positive 1, we'll get 3 plus 2 minus 2, which is positive 3. Function's increasing there, which tells us that we have a maximum at negative 1.2, a minimum at 0.5. So we'll write that over on the other side here at the top. So maximum at f at negative 1.2. And when you let x equal that in the original equation, you'll get approximately 2.1. A minimum at f at 0.5. And when you let that equal x in the original, you'll get approximately negative 0.6, approximately. So the last thing we do is we'll find our second derivative, the critical number of that, and this will tell us if we have, or what our concavities are, and if we have a point of inflection. So d squared x over dy squared will be 6x plus 2. It's the second derivative. The Critical number for that will be where that equals 0, where 6x equals negative 2, and x equals negative 2 over 6, or negative 1/3. So a number to the left of negative 1/3, like negative 1, the second derivative will be negative, which means it's concave down. To the right of negative 1/3, like 0, second derivative is positive, so it's concave up, which also tells us that we have an inflection point at f at negative 1/3, which is approximately 0.7. So that's all we need to sketch our graph. So first thing we have is we have our x-intercepts at 0, negative 2, and 1. We have a maximum at negative 1.2, comma 2.1. We have a minimum at 1/2, comma negative 0.625. And we have an inflection point at negative 1/3, comma 0.74. So the graph will rise up to that maximum point of inflection there, go through the x-intercept, go to the minimum, and then up through the last x-intercept. So there's the sketch of that graph. So in 30-1, we only learned intervals of increase, decrease. We found our x-intercepts. We could kind of guesstimate where the max and min points were, especially where the x value was, but we had no real way of finding where the y value was unless we guessed what the x value was and then plug that number in. But there was some guesswork there, and certainly we had no way of knowing whether the graph was concave up, concave down, or where point of inflection lied. Right, so derivatives help us with all those things. So on the next page, we have 3x to the 5th, take away 5x cubed. Again, there are no restrictions on the variable here because there is no denominator. Another reason why you may have restrictions if you have a square root function, which we don't. This is just a polynomial function. So the domain goes from negative infinity to positive infinity. Our intercepts, x-intercept is again where y equals 0, where 3x to the 5th minus 5x cubed equals 0. So there is a common denominator here of x cubed, which leaves us with 3x squared minus 5. And the x-intercepts come where each of those factors equals 0. So 3x squared will equal 5. X squared will equal 5/3. and x will equal plus and minus the root of 5/3. And if we use our calculator to get an approximation of that, the root of 5/3 is approximately 1.29. Okay, so there's our intercepts. Once again, there are no asymptotes here because it's not a rational function. If we find our first derivative, so the function is y equals, so dy by dx. The first derivative will be 15x to the fourth minus 15x squared. And we want to find the critical numbers for that. By factoring, there's a common factor of 15x squared, which leaves us with x squared minus 1. So again, our critical numbers come when each factor equals 0. And for the first factor of 15x squared, that'll be when x equals 0, where x squared minus 1 equals 0. So that'll be where x squared equals 1, and x will equal plus and minus root of 1, or plus and minus 1. So we have 3 critical numbers here, so 4 intervals that we need to look at. Right, this has an odd degree, a positive initial term coefficient, so once again it'll fall to the left and rise to the right. But if we use a number like -2, let's say in the derivative, well, the first factor, 15x squared, is always going to be positive. When x is -2 and you square all that, you're going to get 4 minus 1, which is +3. So this confirms that the function is increasing in that first interval. What would we use next, Brighton? If you only meant it. Sure. -1/2. Now the first factor is always positive, but the second factor will be negative, because when you square -1/2, you'll get 1/4. Take away 1 is negative, so the function is decreasing there. And the same thing will happen in the next interval. If we use +1/2, we're still going to get a negative value for the second factor. A number greater than 1, they'll both be positive, so the function is increasing there. So the fact that the function is decreasing on either side of 0 tells us that it's not a max or min point. It's actually going to be a point of inflection, which we'll confirm when we use our second derivative. Because you see, when we factored the original expression, we had a factor of x cubed. And remember in 30-1, we learned that when a factor is cubed, that has a multiplicity of 3, there's a point of inflection there. We will confirm that using the second derivative, but we did learn about that in 30-1. But before we go there, we have a maximum at f at -1. And when x is -1, you'll get +2 in the original function. We'll have a minimum at f at +1, which works out to be -2. So now let's find our second derivative. So from the first derivative, we differentiate again, we'll get 60x cubed minus 30x and we want to find the critical numbers for that. There's a common factor of 30x there, which will give us 2x squared minus 1. Again, there's our critical number of 0, which we already know there'll be a point of inflection there, so the concavity will change. But also where 2x squared minus 1 equals 0, which is where 2x squared equals 1, x squared equals 1/2, and x will equal plus and minus root of 1/2. So we'll need to know approximately what those values are so that we can set up our number line. The root of 1/2 is approximately 0.707. Plus and minus 0.7. So there's our 3 critical numbers, gives us 4 intervals. A number to the left of negative 0.7 like -1, well, the first factor will be negative. The second factor will be positive, which means the graph is concave down in that interval. Between negative 0.7 and 0, a number like negative 0.5, again, the first factor is negative. Negative 0.5 squared is positive. 1/4 times 2 is 1/2. Take away 1 is negative 1/2. And a negative times a negative is a positive, so the graph will be concave up in that interval. When x is positive 1/2, you're going to get a positive times a negative, so the graph is concave down in that interval. And greater than 0.7, if x is positive 1, they're both positive, so the graph is concave up. So we have inflection points at f at negative 0.7, which is approximately 1.2, f at 0, which is 0. Again, we already knew that the point 0, 0 was going to be an inflection point because the original polynomial had a factor of x cubed. And then the last one was at f at positive 0.7, which is negative 1.2. So that gives us all the information we need to sketch our graph. So first we had x-intercepts at 0, plus and minus 1.29. Again, because the x-intercept is 0, that's our y-intercept as well. We had a maximum at negative 1, 2, a minimum at 1, negative 2. We had a point of inflection at negative 0.7, 1.2. At 0, 0, and then at positive 0.7, negative 1.2. Again, this function rises to the left and falls to the right. So it comes up to that maximum, There's a point of inflection there, point of inflection there, point of inflection there, down to the minimum, and then rises to the right. Okay, so there is the graph of that function. So we didn't graph any fifth degree polynomials in 30-1, so again, the use of the first and second derivative is a real advantage. So this next one, now we have a rational function to look at. And in this case here, even though we have a rational function, there are no restrictions on x. Because no matter what x is, when you square it, it's always going to be a positive value. And then you're going to add 1. It can never be 0. Our domain is still all real numbers, or from negative infinity to positive infinity. If we look for our intercepts, our x-intercept is where y equals 0. And remember that a rational function equals 0 when the numerator equals 0. The numerator is a constant. It can never equal 0. So there is no x-intercept. Because the x-axis will be a horizontal asymptote. We'll have a horizontal asymptote at the line y equals 0. But there is no vertical asymptote because there are no non-permissive values. The y-intercept, we can find that. It's where x equals 0. So that'll be where y equals 1 over 1 plus 0 squared. So you're going to get 1 over 1, which is 1. The y-intercept is the point 0, 1. So now we will find the first derivative, f prime x, which would need to be done using the quotient rule. Derivative of the top times the bottom minus derivative of the bottom, which is 2x, times the top, all over the bottom squared. So you're going to get 0, take away 2x, or negative 2x, over 1 plus x squared all squared. And the critical numbers for this come where it equals 0 as well as where it's undefined, but there is no place where it's undefined because the denominator cannot equal 0. So a rational function equals 0 when the numerator equals 0, so that will be where x equals 0. That's our only critical number for this function. A number to the left of 0, let's say negative 1, so the top will be negative 2 times negative 1. It'll be a positive. The bottom is always positive, so the function is increasing in that interval. After 0, a number like positive 1, the top will be negative 2 times 1, which is negative. The bottom is always positive, so that will be decreasing in that interval. And so we're going to have a maximum at f at 0. And when x equals 0 in the original equation, That's actually going to be where our y-intercept is, right? The y-intercept is where x is 0. We already know that's at the point 0, 1. Okay. Second derivative. F double prime x. So from the first derivative, we take the derivative of the top, which is negative 2, times the bottom, which is 1 plus x squared all squared, minus the derivative of the bottom, which we must use the chain rule for, which has two pieces to it. The power rule first, times the derivative of what's inside, which is 2x, times the top, which is negative 2x, all over the bottom squared, which will be 1 plus x squared to the fourth. And because there's at least one factor of 1 plus x squared in all three terms, that's where we'll start. We'll divide all three terms by one factor of 1 plus x squared. So this gives us negative 2 minus 2x squared. Negative 2 times 2x is negative 4x, times negative 2x will be positive 8x squared over 1 plus x squared all cubed. And this simplifies to 6x squared minus 2 all over 1 plus x squared all cubed. And we want to find the critical numbers for that, which is where it equals 0 or undefined. There is nowhere that it's undefined. There is no non-permissive value for the denominator. So our only critical number for this will become where the numerator equals 0. So that'll be where 6x squared equals 2. That'll be where x squared equals 2 over 6 or 1/3. And x will equal positive and negative root of 1/3. Which we will use our calculator to find out what that is approximately, so we can set up our intervals on the number line. So approximately plus and minus 0.6. Sure, I'll take one, thank you. So a number to the left of negative 0.6, like negative 1. So the top will be positive because negative 1 squared, negative 1 squared is positive 1 times 6 is 6, take away 2, positive 4. The bottom is always positive, no matter what, because that x is squared in the denominator. You're going to add 1, which is just going to make it bigger to the power 3, also bigger. So the graph is concave up there. In the next interval, if you use a number like 0, we're going to have a negative over a positive. The graph is concave down. Greater than 0.6, like 1, again, you'll have a positive over a positive, so the graph is concave up. So therefore, we have inflection points. At f at negative 0.6 and f at positive 0.6. And when you let x equal those numbers in the original expression, you're actually going to get 3/4 for both of them. Again, you would use the exact value, which was the root of 1/3. Now what, Brighton? Don't say sorry again. So now we can graph the function. We have everything we need. There is no x-intercept, but there's a y-intercept at +1. Now, if we look at all the other points that we have to put on here, we have a y value of 3/4 for our inflection points. And that's the only other y value we have on here except for our y-intercept of +1. So what I'm going to do is I'm going to use a scale of 1/4 on the y-axis. So this will be a half, and that'll be 1 up there, which is where our y-intercept is. We have a inflection point, and I'll use the same scale on the x-axis, so that'll be actually -1/2 and -1, +1/2 and +1. So at -0.6, which is a little less than -1/2, we're at 3/4, which is right there. That's a point of inflection. And then at +0.6, we're also at +3/4. Right? We said that the horizontal asymptote was the x-axis, so we can put that on there. And the graph is concave up in that first interval, plus we know that it's approaching that asymptote. So it's going to come up to the point of inflection, to the maximum, and then go down to that other point of inflection, and then approach the asymptote. And they do a bit better job of that. Okay, something like that. Okay. All right, so this last one today. This one does have vertical asymptotes. Remember that the non-permissive values occur where the denominator equals 0. So 1 minus x squared, where that equals 0. That's where 1 equals x squared, or x equals plus and minus 1 when you take the square root of both sides. So those are our vertical asymptotes. Our domain, if I use set notation, all values of x such that x cannot equal either positive or -1, but all other real numbers will work. And so again, there's our vertical asymptotes. And because in this case the degree of the top and bottom are the same, They're both x squareds. Our horizontal asymptote can be found by dividing the coefficients of those x squared terms. Our horizontal asymptote will be where y equals 1 over negative 1, or y equals negative 1. Remember, when the degree of the top and bottom are the same, we just simply divide the coefficients of those terms to get the horizontal asymptote. All right, our x-intercept is where y equals 0, and because we have a rational function, that will equal 0 when the numerator equals 0. So it's where x squared equals 0, which is where x equals 0. There's only one x-intercept, and that's at 0, which will also be our y-intercept as well. So we can say that our intercepts are at 0, 0. And that's the only one. So next we'll find the first derivative so that we can find our intervals of increase and decrease. So that'll be f prime x that we will have to use the quotient rule for. So the derivative of the top is 2x times the bottom, which is 1 minus x squared, minus derivative of the bottom, which will be negative 2x times the top, all over the bottom squared. And in this case, there is not a factor of 1 minus x squared in all three terms. So we cannot cancel anything. We just have to go to simplifying. So that'll be 2x minus 2x cubed plus 2x cubed. The minus minus becomes a plus positive, all over 1 minus x squared, all squared. The 2x cubes cancel, so we're left with 2x over 1 minus x squared, all squared. And our critical numbers for this will be where it equals 0, which is where the numerator equals 0, and also where it's undefined, and in this case that will be where x equals plus or minus 1. Now we already know what's happening at plus and minus 1. That's where our vertical asymptotes are. Plus and minus 1 are the non-permissive values of the original function. So there won't be a max or min there, but we still want to know whether the function is increasing or decreasing in those intervals. So we will still use our number line, because we want to know whether the function is increasing or decreasing in the intervals. So we're going to have negative 1, we're going to have 0, we're going to have positive 1. To the left of negative 1, a number like negative 2. Well, the first derivative is our 2x over 1 minus x squared all squared. The bottom's always going to be positive, because no matter what you get inside the bracket, you're squaring it. But the top will be negative when x is negative 2. So that means the function is decreasing in that interval. Between negative 1 and 0, a number like negative a half, it'll also be a negative over a positive. So the function is still decreasing there. And remember, at negative 1 is where our vertical asymptote is. When x is greater than 0, like positive a half, it's going to be a positive over a positive, so the function is increasing there. And same thing when we choose a value of x greater than 1, like positive 2. So the only place we're going to have a max or a min is at 0. and that will be a minimum. But we already know at x equals 0, because that's what we use to find our y-intercept, that's 0, 0. Okay, so now we'll use our second derivative to find concavity and see if there's any inflection points. So from the first derivative, the derivative of the top will be 2 times the bottom minus the derivative of the bottom, which we must use a chain rule for, which has 2 parts. The power rule is used first. Then we multiply by the derivative of what's inside, which is negative 2x. Then we multiply the top, which is positive 2x. All over the bottom squared, which is 1 minus x squared to the 4th. And now we have at least one factor of 1 minus x squared in all 3 terms. So we can cancel one factor of 1 minus x squared. So if we simplify what we're left with, we'll have 2 minus 2x squared. Negative 2 times 2x is positive 4x, times 2x is positive 8x squared, over 1 minus x squared all cubed, which gives us 6x squared minus 2, all over 1 minus x squared to the power 3. I'm sorry, that should be 6x squared plus 2. And we need to find our critical numbers for this. And they will be where it equals 0, or where it's undefined, which is, again, plus and minus 1. We already know that that's where we have our vertical asymptotes. So there will not be points of inflection there, but we still want to know the concavity. But first, 6x squared minus 2 equals 0. That's where 6x squared equals 2. It's where x squared equals 2 over 6, or 1/3. And x will equal plus and minus root of 1/3. So again, we're also going to have, and the root of 1/3 is approximately 0.6. But we're also going to have negative 1 and positive 1, because those are the non-permissive values. Now again, we already know that at negative 1 and positive 1, the function has vertical asymptotes there. So there will not be points of inflection there, but again, we still may want to know whether it's concave up or concave down in those intervals. So the top is always going to be positive. No matter what x is, you're going to square it, which is going to make it positive. You're going to multiply by 6, which is going to make it bigger. And then you're going to add 2, so it's just going to get bigger. So the top is always positive in each interval. What we're concerned with then is whether the bottom will be positive or negative. And that will change. A number greater than negative 1, like let's say negative 2. Negative 2 squared is positive 4. 1 take away 4 is negative 3. Cubed is still negative. So the graph is concave down in that interval. Between -1 and -0.6, a number like 0.7. Well, the top is always positive. The bottom will be positive as well, because if you go 1 minus 0.7 squared, that gives you a positive decimal. You're going to cube it, so it's still going to stay positive. And so the graph is concave up there. Same thing between -0.6 and 0.6. A number like 0, it's still going to be positive. So the graph is concave up there as well. Between 0.6 and 0.1, a number like 0.7, well, that'll be positive. So the graph is concave up there. But after 1, the denominator will be negative. So the graph is concave down. So we've got places where it changes concavity at -1 and then at +1. But remember, those are where our vertical asymptotes are. So there are no inflection points, because it only changes concavity at plus and minus 1, but we already know that's where our vertical asymptotes are. So we now have everything we need to sketch this graph. We do know that we have vertical asymptotes at plus and minus 1. We know that we have an intercept at 0, 0, which is also the location of a minimum point. We have a horizontal asymptote at y equals -1. Again, we have only one minimum point, that's at 0, 0. We don't have any maximums. We know the graph is concave down in that first interval. So it will look something like this. And just to confirm that you're in that lower left quadrant, you could take any value of x less than -1, say -2, and plug it into the original function. When x is -2, -2 squared is 4 over 1 minus 4 is -3. So when x is -2, y will be -4/3, -1 1/3. When x is -2, y is -1 1/3. So that's actually going to be down here somewhere. So that's a better sketch. In the next interval, it's concave down and then concave up. So it comes down to this minimum point where it's concave down and then it goes concave up, approaching those asymptotes on either side. In the last interval, once again, it is concave down. To confirm exactly where we are, we can choose a value of x greater than 1, like +2. If x equals +2 in the original function, you're going to have 2 squared, which is 4, over 1 minus 4. You're going to have, once again, -4/3. +2, -4/3 is right there. The graph is concave down. It's got to go through that point and then approach the asymptotes. So there's a sketch of that graph. You can work on for practice page 240, questions 1 through 4. I will post those solutions to Google Classroom so you can check your answers.